Okay, so we're on page 8 in the packet. We're going to talk about half-life doubling and tripling formulas. So as you can see, the half-life formula is an exponential formula. So notice our final amount is equal to, now a sub 0. That could be confusing. So that's why we like to sometimes just change that to p, our principal amount. 1/2 represents the half-life, raised to the time over how long the half-life is. So the best way to compare this or to talk about this is to talk about radioactive elements. Radioactive elements have a half-life. So pulled up a nice picture here. So you have your cobalt 60, your CO60. So you don't have to know what this element is, but just to make it relatable, this is a synthetic radioactive isotope for cobalt, and they use it to treat cancer. And then this has a half-life. So this has a half-life of 5.27 years. So if you notice, 100% of the element will exist at the first exposure. And then after one half-life, so after 5.27 years, you'll have half of the element. And then after another 5.27 years, you'll have half of that half. And the element will just keep taking half of the existing amount. All right, so when we're talking about a half-life of an element, we can figure out how much of the element would still exist after a certain amount of time. So let's flip over to page 9 and let's look at the first question. So element X is a radioactive isotope such that every 94 years, its mass decreases by half. Given that the initial mass of the sample of element X is 40 grams, how much of the element would remain after 13 years? And then round to the nearest whole number. All right, so we're going to write our formula first. A equals principal amount. It has a half-life raised to the, and then we had time over half-life. So that's exactly what we had over here. All right, so my principal amount, my initial amount, the element X starts at 40 grams. Okay, now these are two different time values. This could be a little confusing because this represents the amount of time that has passed. So our T in this example is 13 because 13 years have passed. Our 94 represents our half-life. So after 94 years, the element will be at 20 grams. But we're not going 94 years, we're only going 13 years, so we want to know how much would exist after 13 years. So 13 over 94. And then we throw this into our calculator to say how much of the element would exist. So we have 40 times 1/2 raised to the 13 over 94. And you can, of course, use alpha y equals for these to make fractions. So to the nearest whole number, 36 grams of this element would still exist after 13 years. Okay, so now likewise, you can use this formula in a very similar way for things that will double after a certain number of years. So let's actually skip and look at number 3. So number 3, in a lab experiment, 350 bacteria are placed in a petri dish, and we know bacteria is going to grow. The conditions are such that the number of bacteria is able to double every 6 hours. How much bacteria will there be after 14 hours? And then again, to the nearest whole number. All right, so I'm going to write my formula. So my final amount is equal to my principal amount. Now my base is going to be different. This question is a half-life, which means that this element would have half of its mass after its half-life. This, the bacteria is going to double. So because the bacteria is going to double, I'm going to make the base 2. So I write the formula. See, it's very similar. It's the half-life formula. The only difference is that the base is a 2 when the bacteria is doubling, and the base is a 1/2 when you're talking about something that will have half its mass or a half-life. Okay, so now we can plug our numbers in. So we're starting out with 350 bacteria. Now, again, 2 different time measurements. T represents the time that has passed. So they want to know how much bacteria will be there after 14 hours. So 14 hours have passed. But the bacteria doubles every 6 hours. So that means that its doubling life is 6 hours. This one, we wanted to know what would happen after 13 years when its half-life was 94. Okay, so we have what's going to happen after 14 hours when its doubling life is 6 hours. Okay, so again, we're going to go into our calculator and we're going to type in 350, that's what it starts with, times 2 raised to the alpha y equals, I can make a fraction, 14/6. To the nearest whole number, we'll have 1,764 bacteria after 14 hours. Which makes sense if you think about it, because its double life is 6. So that means that it's going to double after 6 hours and then double again after 12 hours. So actually, let's just do this on the side just to look at it. So it starts with 350. After 6 hours, it's going to double. So that means another 350. So that means that we have 700 bacteria after 6 hours. After another 6 hours, so that means a total of 12. It's going to double again, which gets me 1,400. Now, I wanted to play it out to 14 hours, which makes sense because after 12 hours, if you have 1,400, makes the sense that you're going to have, after 14 hours, you'll have 1,764.